In today's lecture, we will see type 2 problems on Cayley-Hamiltonian theorem. We will see how Cayley-Hamiltonian theorem is used effectively to find the matrix represented by the given polynomial. Okay. Now, in this example, first of all, we will try to find the characteristic equation of A. So here, as you all know, to find the characteristic equation, we want determinant A minus lambda I equal to 0. We need to solve this determinant. So if you solve this determinant, 3 minus lambda 1 minus 1 and 2 minus lambda equal to 0. So 3 minus lambda into 2 minus lambda minus and minus becomes plus 1 equal to 0. So after simplification, 6 minus 3 lambda minus 2 lambda plus lambda square plus 1 equal to 0. So lambda square minus 5 lambda plus 7 is equal to 0. So this is the characteristic equation of A. Here, it is not asked that to verify the Cayley-Hamiltonian theorem. So we are not going to verify Cayley-Hamiltonian theorem, but we can use Cayley-Hamiltonian theorem and we can say that if you replace lambda by matrix A, this is equal to 0. So by CH theorem, we write a square minus 5a plus 7i. We have to write I along with the constant. Okay, when we are writing a matrix equation, constant is replaced by that constant into I. Okay, is equal to 0. So this we can write using Cayley-Hamiltonian theorem. Okay, now we have to prove that or we want to find that the matrix represented by this polynomial, which is 2a raised to 5 minus 3a raised to 4 plus a square minus 4i. So for that, we will consider the given polynomial we will denote it by p of lambda, which is 2 lambda raised to 5 minus 3 lambda raised to 4 plus lambda square minus 4. Okay, and we will divide this p of lambda by the characteristic polynomial. So dividing p of lambda by lambda square minus 5 lambda plus 7, and we will use the standard result that dividend is equal to divisor into quotient plus remainder. Okay, so here dividend is p of lambda, which is equal to divisor is lambda square minus 5 lambda plus 7. We are going to find here quotient is 8 to find plus remainder. Okay, you can see here this value of lambda square minus 5 lambda plus 7, this is 0. So 0 into quotient plus remainder. But 0 into quotient, that will be 0 plus remainder. This implies that we can write p of lambda is equal to only a remainder of this division. or you can replace lambda by a. So P of a means given polynomial in a, which is 2a raised to 5 minus 3a raised to 4 plus a square minus 4i. This matrix is equal to only remainder after division P of lambda by the characteristic polynomial. So I will uh, directly give you the remainder part here. The remainder part is actually 138 into lambda, but in terms of a, we are going to write here 138 lambda minus 403 is the remainder. But when we are writing in matrices, we have to write 138a minus 403i. So answer of P of A, it's simply 138a minus 403i. So finally, it is going to get 11, 138 is the first row. Second row is minus 138 and minus 127. Okay, so this is the use of Cayley-Hamiltonian theorem, and using Cayley-Hamiltonian theorem we can find a matrix represented by the given polynomial. Now here the main part, which is a long division method and how to find the remainder, I will explain in the next slide. Okay, so here I'm going to divide P of lambda. So as you all know, P of lambda is, I'll write here P of lambda, which is 2 times lambda raised to 5 minus 3 times lambda raised to 4. Lambda cube is not there, but I will write here 0 into lambda cube plus lambda square minus 0 into lambda. Lambda term is also not there, but we will write coefficient 0 minus 4. So I'm going to divide this by the characteristic polynomial, which is lambda square minus 5 lambda plus 7. So we need to match actually this 2 lambda raised to 5. So for that, in the quotient part, I'm going to take 2 lambda cube. So if I multiply here, 2 into lambda raised to 5 minus 5 to the 10 lambda raised to 4 plus 7 to the 14 lambda cube. Now you can change the sign here, minus plus minus, and you need to add. So here first term is cancelled. After that, here the 10 minus 3 is 7 lambda raised to 4 minus 14 lambda cube plus lambda square minus 0 lambda minus 4. I have taken from the first row here. Now we need to write in the quotient part 7 lambda square. So this becomes 7 lambda square into lambda square is 7 lambda raised to 4 minus 35 lambda cube plus 49 lambda square. Again change the sign here. First term is cancelled. So here 35 minus 14, which is 21 lambda cube minus 48 lambda square minus 0 lambda minus 4. Now you need to take 21 lambda in the quotient and multiply with this all divisor part. So 21 lambda cube minus 21 into 5 is 105 lambda square plus 21 into 7 is 147 lambda Again, you need to change the sign. First term is cancelled here. So plus 105 minus 148, that will be 57 lambda square minus 147 lambda minus 4. In the question part, you have to take 57 now. So 57 lambda square minus 57 into 5 is 285 lambda, and plus this is 399. Again, you need to change the sign here, and first term is cancelled after adding. So 285 plus 285 minus 147, which is 138 lambda minus 403. So we know that just now we have explained here the divisor part is lambda square minus 5 lambda plus 7, and we know that by characteristic polynomial its value is also 0. Your dividend is p of lambda. Your divisor is 2 lambda cube plus 7 lambda square plus 21 lambda plus 57, and your remainder that is 138 lambda minus 403. So we are interested in this remainder part, and it represent final answer. So we have seen in the previous slide that answer of this is 138a minus 403i, and the matrix represented by it is, I'm going to write it once again, which is 11, 138, minus 138, and minus 127. So in this slide we have seen the actual long division method. So these examples are a simple if it's division part. If you know the procedure of actual division and how to find the remainder, then these examples are very simple. Now we will solve a next example. This is a 3 by 3 matrix I have considered. Again, I'm going to calculate here characteristic equation. So we require trace. So trace is here sum of diagonal elements, which is 5. We require SMD, which is minors of diagonal elements M11, M22, M33. So value of this trace is SMD is 7, and the determinant is here 3. So after finding all these, I'm going to write a characteristic equation, which is lambda cube minus trace into lambda square plus SMD into lambda minus determinant of A equal to 0. So lambda cube minus 5 lambda square plus 7 lambda minus 3 is equal to 0. Now, whatever the polynomial in A they have given, okay, I'm going to divide that with this characteristic polynomial or characteristic equation, and I'm trying to find the remainder. So I'm going to write here dividing given polynomial in lambda by lambda cube minus 5 lambda square plus 7 lambda minus 3, and we will try to find the remainder part. So here remainder is very simple, which is lambda square plus lambda plus 1, and finally a polynomial in A represent a square plus a plus I. So we have to find a square because a we know a, then a square plus a plus I represent here 3 sorry, 855 030 and 558. Okay, now let me explain how to find this remainder part. Okay, so I'm going to explain that part here. I'm going to divide by lambda cube minus 5 lambda square plus 7 lambda minus 3. This is the divisor, and dividend is lambda raised to 8 minus 5 lambda raised to 7 plus 7 lambda raised to 6 minus 3 lambda raised to 5 plus lambda raised to 4 minus 5 lambda cube plus 8 lambda square minus 2 lambda plus 1. So whatever equation, polynomial in A, just you can replace it by lambda just for a division, because we cannot divide actually in matrices part. Okay. So here in the dividend, we have to take lambda raised to 5, and you can multiply with whole terms. So here lambda raised to 8 minus 5 lambda raised to 7 lambda raised to 6 minus 3 lambda raised to 5. Then you can change the sign and you can add here. So here all the terms gets cancelled, all, because they have opposite sign. So it is left now here lambda raised to 4 minus 5 lambda cube plus 8 lambda square minus 2 lambda plus 1. Remaining terms I have written here. Now, in the this quotient part, you have to take lambda, and again you can multiply throughout by lambda. So lambda raised to 4 minus 5 lambda cube plus 7 lambda square minus 3 lambda. Again change the sign here, plus minus, and you need to add here. So first term is cancelled, even second term is cancelled. Then 8 lambda square minus 7 lambda square is lambda square, plus 3 lambda minus 2 lambda is lambda, and plus 1. So this is the remainder. We have used this remainder over here, and we have used the formula that dividend is equal to divisor into quotient plus remainder. And finally, this the value of the divisor is 0 by Cayley-Hamiltonian theorem. So finally we got only a square plus a plus I, and the matrix which is represented by 855 030 and 558. So I hope this application is clear to everyone. Definitely one question they may ask on this part. This question has come many times. Thank you.